Welcome back, my friends. Today we're going to continue talking about real gases and the real gas laws. In this particular video, we'll talk about why gases will deviate from the ideal and how that we're going to treat those and how we're going to calculate those. We'll talk about the critical values, critical constants for a given gas. Couple proofs and we'll be well on our way. Okay. Starting off with the limitations of gas law. Oh, geez, okay. Yeah. Okay. In a second. Yeah, there we go. Move my face somewhere it's not going to be too hindersome. Okay. So the idea here, looking at this curve right here, is a pressure volume curve for gases. And up here, this top curve, each of these curves are looking at different temperatures, looking at a pressure volume curve at different temperatures. And you see up here, the gas has a normal conversion, another normal curve at all pressures and volumes. And then if we look at different temperature, it goes down, it's shifted down a little bit, but it's still normalized. Well, the idea here is the idea that a gas, under the appropriate conditions, will be liquefied. Looking at this PV diagram of various isotherms, you see how the pressure will be affected by the volume. Now, high enough temperatures, as I said, the gas will remain gas and will essentially have an ideal gas. But when we get to a low enough temperature, we're going to see some unusual things. As the volume decreases, there is a region of constant pressure followed by a rapid increase of pressure where very little volume changes. And this is when we start to form liquid gas mixture. So as we're pressing it down, some of the gas liquefies, but some of the gas remains a gas. So a liquid is not really compressible, but a gas is. So as it liquefies, the pressure essentially remains constant as the volume goes down. Then we suddenly hit this point where all the gas has become liquid. And at that point, the second the volume hits, the volume hits the volume of the liquid, pressure shoots through the roof because the liquid is nigh incompressible. So we achieve a point where the critical isotherm, where liquefaction starts to occur. And this point is the critical point. So all these isotherms above this critical point are essentially supercritical solutions. Essentially, it cannot be liquefied no matter what. But once we get to the critical point, we start to see condensation. And as we go down and down, you'll see, oh, you hit this line right here. Suddenly the pressure remains constant as it liquefies and shoots up. Under these really low temperatures, you will see a greater portion of this line will liquefy at a higher volume at lower temperatures. And so you will see a greater portion of this. But so we have to be able to deal with that. And that's where the curve comes in. So now one thing to note, there's a critical temperature. So each isotherm temperature, there's a different sized region of liquid vapor mixture corresponding to the pressure. Now, the temperature-dependent equilibrium pressure above the liquid is called the vapor pressure. So the vapor phase, when we have some liquid and some gas, we have some vapor pressure. But basically, as temperature increases, the size of this region decreases until we get to a single point, which, as I said, our critical point and our critical temperature. Now, why is that super important? As I said, above the critical temperature, it becomes supercritical fluid. It will not liquefy. Gas and liquid phases become indistinguishable. Now, to become a supercritical fluid, we have certain critical constants. We have a critical pressure, we have a critical temperature, and a critical molar volume. So they come together on the exact point for this critical point. Where we look at this, if we look at this and look at the derivative of this, at that critical point, the isotherm, the change in pressure versus the change in molar volume is 0. So saying the increase of the change in our slope is 0 at that point. Going from left to right, blah, 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 blah. We have a constant thing, and suddenly it reaches a point where there's no change. But also, the change in the change, the acceleration of how the pressure changes with volume is also 0. So this is a true inflection point. So defining that. So saying that the rate of change of pressure and volume is 0 at the critical temperature and the critical point, and the rate in the rate of change is also 0. So instead of going up and then some going down, it's going up, stopping, and going up again. But so one of the cool things here is that the parameters A and B for the van der Waals equation and for the Redlich-Kwong equation are chosen to represent a real gas, and they're done using these gases' critical pressures, critical temperatures, and critical molar volumes. Because of the statement that at the critical point, these two statements, that the rate and change of pressure versus volume is 0, and the rate and change of the rate of change of pressure and molar volume is 0. We're going to actually use this statement and the critical pressures to solve what are A and what are B in regards to those critical constants. So pull that down so I can pull up this and work on a proof. Not a pretty proof, but it's a proof nonetheless. So this is a multi-part proof. So brush up your proofing sleeves. So in part 1, and we're going to use just the van der Waals. We have to state that first the change in dP over dVm at our critical temperature is equal to 0, and our d squared P over dVm squared is equal to 0. And that's our starting statement. And that at the critical pressure, RT critical or VM critical minus B A over VM critical squared. So there is our van der Waals equation of state in terms of the critical volume. So modeling the van der Waals gas under all critical solutions. So let's look at what would the first derivative of this be. Because the first derivative of this with regards to molar volume, with regards to pressure being Y, is equal to 0. So we have to do a first derivative of one of this. So 0 equals, well, the derivative of Vm, it would be 1, but the 1 over Vmb becomes negative 1 over Vm b minus b squared. So we get the RT is carried through unchanged because it's a constant, but we have to do derivative by parts. So we have to do this part first. So this whole thing, x to the negative first, the derivative of that becomes negative x to the negative second. And then the second part, the Vm, just goes to what? Vm. Just goes to 1. So that's not a part. Now the next part, the Vm cubed. So the a carries through, and this becomes negative 2 carried out. So negative 2 times negative 1 is positive 2a over VMC cubed. So that is a statement for the first derivative. That has to equal 0, whatever that is. And we're going to solve this for RTC. So we get RTC on the other side. So we subtract 2a over VMC, and then we multiply both sides by VMC minus b squared. So we're getting this to the other side and say RTC equals 2a over VMC cubed VMC minus b squared. So we have the way to exchange RTC for those. So, see if I can add a room. So I'm going to go ahead and clear this. Wish I could just make more room, but actually, well, I'll select this and just delete all. Delete that again. Now let's looking at the second derivative. The second derivative was also equal to 0. Second derivative of that, so 0 equals RTC over, so you take the derivative of the derivative, so derivative of the derivative, this becomes, well, let's positive, so that's 2 RTC over VMC minus b cubed, and that goes back to negative again. So negative 2 times 3 is 6a over VMC to the 4th. And once again, solving for RTC. RTC equals, so 6a over VMC squared. 6a over VMC to the 4th times VMC minus b to the 3rd, all divided by 2. So that cancels, and that puts us at 3. Now with that in mind, I can plug that RTC into this RTC and solve them. I'm going to plug the first into the second. So I'm going to delete the thing up here. So with that in mind, we have 3a over VMC to the fourth VMC minus B to the third must also equal 2a VMC to the third VMC minus B squared. So let's cancel out things that duplicate. So cancel those out, and this whole thing goes away. Cancel them out, all those things go away. So let's erase this, and so let's simplify. So we have what's left. If I divide then 3a, both sides have 2/3. Let's see. We have, sorry, I'm gonna leave the divide both sides by a and get the VMC to the other side. So I have 3 VMC minus 3b equals 2 VMC full stop. So what, once again, subtract, cancel, and separate. So you get that VMC equals 3b, or essentially that the constant B is equal to your critical molar volume divided by 3. Either one is acceptable. Either stop there or there. So we right now, if we can determine a gas's critical molar volume, we have a way of determining the minimum molar volume of gas. How small can a gas get? Select all. Okay. We can determine how small a gas can get just by that. Now, plugging this back in to our equation, or back to our equations, we can now solve in terms of A. So just going back into our first derivative. Our first derivative, remember, our first derivative was this, 0 over negative RTC over VMC minus B squared plus 2a VMC. So let's plug VMC in for, let's plug in 3b in for VMC to completely get rid of VMC. So with that in mind, plugging that, you get negative RT over T critical 3b minus b, also known in most circles as 2b squared plus 2a over 3b cubed. All that's equal to 0. So let's simplify and solve in terms of T critical. So negative RT over 4b squared plus 2a over 27 b cubed. Get that to the other side. So you have, moving up, negative 2a over 27b cubed times 4 times negative 4e squared. Cancel those out. So you have that RT critical. So we're going to get the R to the other side. So we have literally 8A over 27RB is equal to our T critical. So we found T critical in terms of A and B. Now finally, we're going to plug this in for our original equation, the van der Waals equation of state. So select all and solve everything in terms of P critical. So we have our original equation of state where P critical is equal to RT critical over VM critical minus B minus A over VM critical squared. So remember, this was our 3B. So plugging in, and TC was our 8A over 27RB. So we have 8A times R 27RB all over 3B minus B minus A over 3B squared. So 9B squared. So 2B there. So simplify all this in terms of P critical. Put this together and simplify. So 2B cancels out. So we have what, like, equals what, like 2B, 8 divided by 2 is 4, so 4A over 27B squared minus A over 9B squared. Well, let's get these into the same factor, so I'm going to multiply by 3 over 3. So you simplify P critical down to A over 27B squared. So there's our, we now have all of our substitutions for our ideal gas. We now know how to define our terms of A and B in terms of the P criticals. So since the critical pressure and temperatures can be more accurately measured, we're going to try to solve A and B in terms of only those two constants. And so we're going to now change things around. Instead of having the A and B equal those, we're going to find just A in terms of T critical and P critical. So that was a whole hell just to get there. Now we're going to take it one step further to solve those guys just in terms of these. So let's select all. So we have our 3 terms. So now, knowing that P critical is equal to A over 27 B squared, that T critical is equal to 8A over 27 RB, and VM critical is equal to 3B. We're going to try to get just A and B in terms of those guys. So we're going to solve A and B using just critical variables, and we don't want to use molar volume because that's too inaccurate. So that in mind, you can either solve for A using one of these variables, or solve for B with one of these variables. Either one will work. You can either say like, oh, A is equal to 27B squared P critical, or you can say that, oh, or you can say that, oh, B critical, oh, B is equal to 8A over 27 RT. Either one will work. So using that in mind, we're going to plug this back into our original van der Waals equation state, so our P critical. So P critical equals, our rewriting the equation, just as a quick reminder where we're going from. That's A over VM squared. Okay. So we're going to start by plugging our molar volume in. Our molar volume in, because we want to get rid of that. We don't want any molar volumes in there. So let's, and I'm going to go ahead and plug in our A, as we just said right there. So we have RTC, molar volume is 3B minus B, so 2B. Then we have for A, it's 27B squared. Oh, 27B squared P critical, all over what, like 3B squared, so 9B squared. So those cancel, and that 9 cancels to give us 3. So 3P critical. All that's equal to P critical. So that in mind, add the 3P critical to the other side. So we have 4P critical equals RTC over 2B. Get 2B to the other side. So you have, and get P critical back over there. So you have B equals RTC divided by 8P critical. So right now, we just found B in terms of only P critical and T critical. So we don't have to use those other values. We don't have, so right now, okay, we're going to do this again. Now solving for A. Same starting point. So we're going to say, oh, P critical is equal to RTC. We've already removed, I'm going to go ahead and remove the VMC, critical molar volume, because we really don't want that. Okay. From that same starting point, now I'm going to plug in the B. We just determined the B to be what? RTC over 8PC. So this becomes what? RTC 8PC. So that simplifies to what, like 4 PC. And this also you're going to have what, like minus a, let's see, 64 PC squared over 9 RTC squared. Okay, and that's all equal to PC. So let's get PC onto the other side. So we have literally negative 3 PC equals negative 64A PC squared over 9 RTC squared. So let's divide both sides to get A by itself. Well, PC cancels with one of the PCs. So we're going to have, okay, let's get this. So we have A equals RTC, all that's squared. 9 times 3, 27, divided by 64 PC. So that's a hot, ugly mess. You have A equals 27 R squared TC squared over 64 PC. Now, is that easy? No. But if you know the critical temperature, we know the critical pressure, you can, and R is always usually given, we can quickly calculate what is A without having to look it up in the book. If we know those two values, we can find out A. If we know those two values are the PC and TC, we can find out B without too much difficulty. So this is how you would systematically find these, and this is how they were all found as they put in the appendix. Now we could do that exact same steps when we look at Redlich-Kwong. We would have to use the Redlich-Kwong equation of state, and it would be a much, much bigger pain in the butt. However, it could be done. If you know that the T critical is 150.86 and the P critical is 48.98, determine A and B for argon. And A, let's say A is done, A is calculated with in bars. So R is going to be just 0.08314. So merely for to calculate B, it's going to be 0.08314 times 150, and divided by 8, divided by 48.98. And you'd get, well, it's 0.0318. Oh, actually, sorry. So okay. Yeah, let's say 0.032009, which rounds up. It's pretty close to the one in the back of the book, which is 0.0320. Let's do it again. 27 times 8 times 0.08314 squared times 150.86 squared divided by 64 divided by 48.98. Get 1.35 355, and that matches the 1.355. So this is how you can calculate these without a book in front of you. It's possible to calculate that by measuring the critical temperatures. So that's as far as we're going to get right now. The last thing we're going to look at is when we come back, last thing we're going to look at is the universal gas law, ways how we're going to treat gases as a general gas rather than as each individual gas. And eventually we're going to look at fugacity, which is kind of like an activity coefficient for gases.